Welcome, everyone. I'm your host, and with me is Kai, our lead expert and innovation catalyst here at Idea Mechanics. Today, we're diving into a concept that's going to flip how you think about engineering right on its head. Get ready, because we're about to explore the incredible power of engineered emptiness. Let's get into it. We're all taught to believe that big breakthroughs come from these random eureka moments. But our catalyst, Kai, is here to show us that's a total myth. See, real game-changing innovation isn't about waiting around for lightning to strike. It's about building a system for it, a process you can actually count on. And one of the most powerful systems for that is something called TRIZ. Now, simply put, TRIZ is a methodology that takes innovation out of the world of random guesswork and turns it into a structured, repeatable science. It's all about creating a real culture of systematic discovery. And speaking of that, if you're ready to stop relying on pure luck and really start mastering systematic discovery, go ahead and hit that subscribe button to join the Idea Mechanics team. Yeah, and don't forget to ring that notification bell so you're the first to know when our next innovation breakdown drops. We want to build this culture with you, so drop a comment below and tell us which TRIZ principle or tech challenge we should tackle next. All right, let's jump in. Today, we're focusing on one of the most elegant principles in the entire TRIZ toolkit, Principle 31, Porous Materials. And trust me, this is so much more than just, drilling a few holes in something. This is a fundamental mindset shift in how we solve problems. So as Kai is showing us here, the old way is often, it's kind of clumsy, right? You've got a problem, so you just bolt on a heavy, complex fix. But the TRIZ way? Oh, it's so much more elegant. Instead of adding more stuff, we engineer the material itself with porosity to solve the problem from the inside out. We are literally making the material smarter. So, how does this actually play out in the real world? Well, our first case study is going to take us into the high-stakes world of electronics manufacturing, where one tiny microscopic error can cause a total disaster. The big challenge here is what you might call the chaos of assembly. Just a single tiny drop of extra solder can form something called a solder bridge. And that little bridge creates a short circuit that can completely fry an incredibly expensive component. For manufacturers, this is a massive, costly headache. Okay, now check out this solution. Instead of trying to mechanically scrape away the extra solder, they apply a porous metal mesh. And watch here, as Kai shows us on the diagram, those tiny empty spaces in the mesh create this powerful capillary action. It works like a super high-tech sponge, instantly vacuuming up all that excess molten solder. And that right there is the brilliant win. A simple, porous element gives you a perfect, clean solder joint every single time. It just wipes out the short circuits and solves a huge manufacturing bottleneck. It's systematic, it's repeatable, and it's so much better than just guessing. Okay, let's move on to our next case. Now we're tackling a problem that every engineer faces. How in the world do you keep powerful machines cool without weighing them down with all this bulky, inefficient hardware? This is the classic engineering trade-off, power versus heat. The more powerful your motor, the more heat it kicks out, and that heat just kills performance. And the traditional fix? It's always to bolt on heavy pumps in giant radiators, which adds a ton of weight and complexity. But the TRIZ solution here is just genius. As Kai's diagram is showing, a porous material soaked with coolant is built right into the machine itself. So, as the machine heats up, the coolant evaporates out of these tiny pores. That change from liquid to gas absorbs a massive amount of heat. The machine literally sweats to cool itself down. So, here's the key takeaway, right? By engineering porosity directly into the design, you get a super efficient, super lightweight cooling system that's part of the hardware itself. You don't need any external pumps or radiators. The function is elegantly integrated, not just clumsily bolted on. All right, for our final case study, let's look at a problem where even the slightest mistake is an absolute deal breaker: achieving perfect stability in precision engineering. The challenge is simple. How do you get stability without just adding more mass? Because in precision machining, even microscopic vibrations can totally ruin your final product. And the old school solution is just to add heavy external dampers, making the whole system bigger, heavier, and more complicated. But watch this. It's incredible. By making the part itself out of porous aluminum, sometimes called aluminum foam, you create a built-in shock absorber. As Kai is pointing out, when vibrations travel through the material, that whole network of empty pores absorbs and dissipates the kinetic energy, basically neutralizing the vibration from the inside. And the win here is just fantastic. You get a dramatically more stable, higher precision process, not by adding weight, but by systematically removing it. Think about that. You achieve better performance by making the object lighter and basically emptier. It's so beautifully counterintuitive. So what's the big lesson from all of this? What's the main takeaway? It's that innovation is truly an architectural skill. Learning to see and engineer the empty space, the void, is one of the most powerful and honestly underused tools you have. I mean, just think about what we saw. We saw how engineered emptiness solved three totally different problems. For wicking, it managed fluids with precision. For cooling, it made super efficient thermal management possible. And for damping, it absorbed destructive energy. It's the same core principle, just applied in three absolutely brilliant ways. So that really just leaves us with one final thought. I want you to look at the challenges you're facing, the systems you're designing, and ask yourself this one simple but powerful question. Where can you add a whole lot of nothing to create your next breakthrough?